If we could offer you a storage system that is faster than local file system on DAS, think Fusion IO, more resilient than your SAN, gives you better POSIX semantic than NAS, and scales like an object storage and is cloud native, would you be able to use such a product? So we find out that customers can actually use such a product. Our first year in market has been tremendous last year. We've been growing faster than any other documented storage company, because basically what we show customers, we solve storage. We really do. Usually when customers have storage issues, they go to their local storage architect or they go to a VAR. The architect comes in and then they said, hey, that object store is going to be your lake. You're going to use some middleware to copy it to the NAS, but the NAS is not fast enough, so you're going to cache locally, and you're going to buy 3 or 4 different kind of storage solutions and a whole slew of middleware to actually get them to all work together. Luckily for our customers, they just need WekaIO. We take all the complexity away and they get higher performance because they don't have all the hassle of managing their data throughout their workflow. So I'm going to focus now on machine learning. It's the most exciting use case. It's mostly unsolved. So for us, it's a great green field. We go against other vendors that didn't prove themselves, and we win a lot in that space. We also have great successes in genomics, where a lot of people now copy to a local file system, obviously around the financials, which they don't let us tell about anything about what they do. They care about performance, as you may realize, and software build, chip design, DevOps. But I'm going to talk about machine learning. And machine learning is actually quite interesting. The thing about machine learning, people have been thinking about computers making more good decisions for a while. This is the earliest quote I was able to find, but basically NATO was asking, hey, why do we put pilots in planes? It's so dangerous, it's so difficult. And their explanation back then that a human was cheaper than their computers. So a computer was too expensive, too heavy, you wouldn't put it in a plane. They didn't even come to think about the complexity of getting computers to do these kind of things. I found it kind of funny. Then we look at what actually the theory was able to do, and we have this Marvin Minsky, which many consider is the father for machine learning, saying in '67, within a generation, the problem of creating artificial intelligence will substantially be solved. Guess what? He was right. In the 80s, a lot of the theory for deep learning was done. So you had PhD students actually doing deep learning workloads, and they were able to go through an epoch, a one cycle that you're going to see soon how our customers are running through, guess what, 1 semester. So in the 80s, you had enough computational power to take 4 months to finish one run. But you need hundreds and thousands of runs to actually optimize your code. And as you can see here in the 80s, machine learning got into the freezer because it couldn't be done, and it was basically thawed a few years ago with the power of GPUs. And now the question is, hey, this is storage field day, right? Why am I talking about a compute problem? The reason at Storage Field Day I'm talking about the compute problem is because theory shows that the more data that you have, if you want to use the deep networks, the better your models are. So customers get better results the more data they store and the more data they can access. And guess what? Their files are teeny tiny. They don't need large files. If you're looking at the car that has, let's say, 8 cameras around, you can go in the Bay Area, you're going to find these cars. They take 60 frames per second, but really low resolution because you need to find out the line between the lanes, a cat, a pedestrian, the other car. You don't need high resolution. So these files are small, but you got a bunch of them. If you're stuck with NFS-like metadata, you just cannot even go through enough of them in the time. So even if you were able to get NFS to access the data faster, as some vendors are trying to show, the chattiness of the protocol and how the metadata is handled basically prevent them going through enough files. What do customers need for machine learning, for AI? It's similar to HPC workloads. A lot of customers go out, they buy the HPC kind solutions only to find out they don't work. Why? They do require high bandwidth. You know, a DGX1, we've showed you a server with one interface doing 11. The DGX1 has 4 interfaces. It could do 44 or 45 if you actually aggregate the half at the end. So it's high bandwidth, but it's not the high bandwidth that you would get from a traditional hard drive-based parallel file system or a scale-out file system. It's high throughput where you get out of reading tons of 100, 200, 300K files. So it's a high throughput based on immense amount of small operations that all have to be low latency, which is a lot harder than what customers are used to be getting from their storage. So this amount of throughputs are immensely harder for the traditional kind of storage. So you need good metadata performance. You need to traverse the file. So I take you back to Shimon's example of untarring locally like a local file system. If you're going back to your NFS example, we actually strategized, hey, should we show an NFS? And we've just said no, it would be just one vendor, but it doesn't matter which vendor it would be. Any NFS-based or the GPFS or the Lustre, you can go home, download the same kernel version, untar it, and see how many long minutes it takes instead of the same 5 seconds that it took for us. So metadata does become very important when you have so many files. You need to host all these files in the same directory. Assuming you have 8 cameras on a car and it takes 60 frames per second, 30 minutes later, you have the 100K files, standard directories that standard storages can hold. But let's say you need to hold all the files in the Bay Area or another region in the same directory because this is really what makes sense. Then you need the hundreds of billions of files we can actually store in the directory.
Ron, you say very high single host performance. You're talking about like a server in that regard?
Yep. So as I said, the DGX1 having 400 gig lengths can go to 45 gigabytes a second.
Yeah, but that's
a single client.
Like 8 servers or 4 servers in it or something like that?
It depends. We have customers that have quite a lot of these, and they run to many, many hundreds of gigabytes per second, and then they have more than 8 servers. We would scale to any kind of performance our customers would need, and then you say, hey, how many of these servers that have 400 gigabit per second I want to run as clients concurrently? So we just unclog any of your bottlenecks. We would support any number you would need with the tremendous amount of the small files that these keep going through. Another important is the ability to say, hey, this is important, this is less important, because these customers have dozens of petabytes of data. Any given point in time, they work on a small portion. We actually provide, as Shimon said, API to their job scheduler that they can say, hey, that job's starting soon. We need these files there. Once the job starts, everything is staged on NVMe. And we have, as Barbara showed in her slide, have integration with most of the job schedulers out there already. So these things are transparent for our customers. This was actually the next platforms. The same summit that we've showed that 2 orders of magnitude smaller cluster did 30% more work, tried actually running machine learning workloads, so not the IO 500 built for the supercomputers, and then they realized, hey, not only for the IO 500 we beat them, they're incapable of providing the performance that they got that system for, because this is a system with 2,700 GPU servers. And just looking at 40 terabyte data set with 200K files, they couldn't run through them. And what they ended up doing at Oak Ridge is actually retrofitting their servers with local storage. They're now copying data locally and they run over them. We would have solved it. Obviously, this is a federal contract that was done when we were in stealth. But they're stuck with a storage system that doesn't solve their problems, and they're actually quite public on it. Again, why are we showing machine learning? Machine learning is just the obvious win for us. There are no other vendors, and we solve it perfectly. Obviously, we are a great fit for other problems as well. And what we see with these customers, they start with machine learning and then they go to doing computational fluid dynamics for the rest of the cars or chip design. Yep.
There's a couple of benchmarks that AI solutions have used, the RefSnet 50 and 100 and stuff like that. Do you guys have those sorts of benchmarks?
Definitely. And what we're showing that for all of them, we're faster than the local file system, which is in turn faster than any of the other vendors that come up with results.
Okay.
So actually, I assume by this time you would have seen enough benchmarks. So we didn't.
Never see enough benchmarks.
You never see enough benchmarks. So across the board, what we show that for training and inference, we're faster than the local file system, which in turn is faster than any other storage provider.
I would say most of the inferencing workloads are fairly trivial compared to the training workloads.
Exactly. And that's where, and actually we're going to see it soon, this is where customers spend most of their time and we provide the most improvement, because you're doing the training, which is the new work, and then you're going through inferencing through thousands of miles that you have written and you want to rewrite them. And most of your win is around the inference because it takes most of their time. And we're actually allowing our customers to buy more GPU servers and drive, if they're driving through more miles, at a shorter clock time. So why does it make sense? A single server has 10 times the performance of CPU servers, actually in many cases more than 10 times, but NFS was never enough for one, so it doesn't matter. Try to get 10 times that performance and you have immense amount of data. So it's a no-brainer to go buy WekaIO for these workloads, because even if you're coming up with a storage solution that lets you field a single large file faster to the server, like the GPFS or the Lustre or other vendors are now trying to show with NVMe over Fabrics or NFS over RDMA, the amount of small files you have to go to break them back to the standard NFS performance because of the NFS chattiness that the RDMA doesn't fix. So NFS is usually NFS is usually limited to about a gigabyte per second. Again, for large files, other forms are slightly better. We actually got this as a gift from a customer. They told us NFS is not for speed, so you shouldn't use it anymore. And switching to us, we can actually get you 44 or 45 gigabyte per second for the DGX1. DGX2 should improve once we put our hands on that. We'll show higher numbers. So you get an NVMe optimized parallel file system that can get you all the throughput out that actually solves your problem. Also, if you need to do some more work on the cloud, we would just tier to the cloud. This is another thing to accompany what Andy said. That's another slide. Caching is futile. We have a shared file system that is faster than your local DAS file system. So we're faster than whatever caching solution you would be able to use. And the reason is our networking protocol is a lot more optimized than the standard TCP/IP. So moving 4K around the network, being 100 gig Ethernet or EDR InfiniBand, takes about a microsecond. If you're looking at an NVMe device, and it doesn't matter what logo, writing to it takes about 30, reading takes 100. So going through the network, we are 2 orders of magnitude faster, basically saying the network is insignificant. Now what we do, we parallelize your IOs in the 4K granularity. So if you just run 4Ks, instead of running them on the single queue that you have locally, having latency increase, we spread them around all the queue. So for 4K, we're better. But now let's say you're running 8K or 16K IOs, we would run them at 2 concurrent 4Ks, way better, or 16 or 4 concurrent 4K. If you're running 64K IOs, we'd run them at 16 concurrent 4K IOs, way better. If you run a 1 meg IO, we'd run them at 16 concurrent 64K, so the SSDs are at throughput. So it doesn't matter what IO your clients are actually running, we'll run it faster than what a local file system can theoretically do. And this is the big thing about our solution. We have figured out a way to aggregate NVMe throughout network and make sure a shared file system is faster than the local file system. This is actually similar to what NetApp did in the late 80s or the 90s, showing they can aggregate hard drives to get more performance out of a file system.
So Liran, does that mean that if you look at the way that you've designed your system, you would recommend that the deployment model would be clients running or hosts running the client software and dedicated storage nodes rather than an HCI model?
It's 100% psychology and preference. If the clients don't need all of the network speed, HCI is a more optimized solution. We actually have machine learning customers running in the HCI mode. And it boils down to preference. I'm not going to tell you what kind of shirt you're going to wear tomorrow, but we support both. And we figured out that if customers like converged, you won't convince them that dedicated is good. If customers like dedicated, you won't convince them that converged is good. We just support both. So there are other like religious decisions. We have quite a few machine learning customers for autonomous driving. TuSimple is one of them. They've tested a bunch of storage solutions. They weren't happy. We're actually able to show them that we were more than 10 times faster than their HPC kind solution they were tested. Our tiering let them save quite a lot of money. When we actually allow them to also move some of their workloads to the cloud, going through these workloads, what's interesting about them, you're going through tons of iterations. Each time you improve quite a bit. Each such cycle, it's called epoch. So the more iterations you run, the closer you get to the solution, and basically you get your product out to market. This is what 100% of the machine learning customers want. They want to run through enough iteration so they have a good enough model that they can sell. And what we're actually showing our customers, and this came from a different customer that unfortunately we cannot name, but they're doing tremendous amount of work in the autonomous driving space. They showed that before we came and they had to copy data locally, a single time to epoch took them 2 weeks. And that's because of all the very difficult pipelines they had. They had to wait for things to end, to continue to the next phase. If one client was behind, the whole dropped. So on average, it took them 2 weeks. After they switched to us, because everything just uses the storage, there is nothing to mess up, and it's faster, we bring it down to 4 hours. So we let them do the work they used to do in a year in under a week, which is insane saving. So it allows them to get a lot more out, and that's the very nice quote we got from TuSimple. where a standard NAS could not scale, and we were the most performant of the all parallel file system.